top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. Design a microscope using a convex objective lens of focal length 10 centimeters and a concave eyepiece of focal length 20 centimeters. The object is to be placed 12 centimeters from the objective lens. The final virtual image is to be 120 centimeters from the eyepiece. The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. The fundamental concept is image formation based on a system of 2 lenses. The next step of the interpretation is to create the model and represent the model in a diagram. Our system consists of a convex objective lens, a concave eyepiece, an object, and a final virtual image. First, we'll show the optical path of light. The light travels along a principal axis, starting at the primary object, through the objective lens, then the eyepiece, and then is detected at the observer. A very important idea in these problems is that as we go along the optical path, we will treat each optical device individually. For that reason, we will number the optical devices in the sequence in which light passes through them. Hence, the object lens we will refer to as lens number 1, and the eyepiece we'll refer to as lens number 2. Therefore, everything relating to these devices will be subscripted using these numbers. In this problem, the objective lens is a convex or converging lens. We will call its focal length f1. The eyepiece is a concave or diverging lens, and we will call its focal length f2. Finally, we're told that the final image, which we'll call I2, is a virtual image. In our representation, we have the light traveling from left to right. So this means that the final image I2 must be to the left of the eyepiece. We'll introduce here our conventions for the distances that we will use. Our primary object, which we'll call O1, is at a distance dO1 from the objective lens. The image distance dI2 is the distance from I2 to the eyepiece. Finally, the length L we will use to denote the distance between the 2 lenses. The third step of the interpretation is to extract the data carefully from the problem. The focal length of the objective lens is 10 centimeters. So we denote that f1 is plus 10 centimeters. We write the plus to emphasize that the first lens is a converging lens. The primary object is placed at 12 centimeters from the objective lens. That is our distance dO1. At this point, we'll introduce our convention for optical distances. Our optical distance, in this case SO1, is dO1 with the appropriate sign. The sign convention that we'll be using in this problem is the real is positive convention. For the real is positive convention, real objects and real images will be denoted by object and image distances that are positive. Hence, our object distance is plus 12 centimeters. Next, we will focus on lens number 2, which is the eyepiece. The eyepiece has a focal length of 20 centimeters. In our data, we will write that f2 is equal to minus 20 centimeters. The reason that we have a negative focal distance is that we are given that the eyepiece is a diverging lens. Finally, we're told that the final virtual image is 120 centimeters from the eyepiece. Geometrically, this corresponds to our distance di2. So di2 geometrically is 120 centimeters. But because this is a virtual image, our optical distance si2 is written as minus 120 centimeters. The first step of the strategy is to determine precisely what is required. In this problem, we are asked to design a microscope. Referring to our model, we have all of the parameters for our microscope except the distance L between the two lenses. Hence, in our solution, we indicate that we are required to find the distance L. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. Looking at each lens in turn, we first look at the objective lens, lens number 1, for which we are given the object, O1, and we're given the focal length, f1. From these, we can calculate the image of lens number 1. A fundamental physical consideration is that the image for lens number 1 must correspond to the object for lens number 2. What determines this coincidence is precisely the distance L between the two lenses. Finally, the object distance and the focal length for lens number 2 give the image distance for lens number 2. In this problem, it is the focal length and the image distance that are given. The third step of the strategy is to create an action plan based on the concept map. The first step of the action plan is to find the image from lens number 1 from the object position and the focal length. The next step is to find the object distance for lens number 2 from the known image distance and focal length. The third step is to use the coincidence between the image for the first lens and the object for the second lens to determine our unknown length L. The first step of the execution is to follow the steps of the action plan. We will use the lens formula shown here, but we will write it in a form that isolates what it is that we're looking for. This being geometric optics, it's very helpful to draw different pictures to show us the quantities that we're looking for. Our first object is placed from the lens at a distance that is greater than the focal length. This creates a real image that is also at a distance greater than the focal length from the lens. So we calculate our image distance SI1. We notice, first of all, that SI1 is positive. This confirms that I1 is a real image. Secondly, we confirm that SI1 is larger than the focal length f1 for this lens. We apply the formula once more for lens number 2. Once more, we draw the ray diagram. We are given that we have a virtual image that lies beyond the focal length of the diverging lens. This is obtained from a virtual object that also lies beyond the focal length of the diverging lens. We substitute once more into the formula, but in this case we isolate the object distance SO2. We obtain that the object distance is negative. This confirms that our object is a virtual object. Finally, we write down the geometric object distance DO2. We observe that in magnitude, this distance is greater than the focal length for lens number 2. For the third step, we invoke that the image I1 due to lens number 1 coincides with the object O2 for lens number 2. As we saw earlier, the image I1 is a real image to the right of lens number 1. The object O2 is a virtual object to the right of lens number 2. We therefore calculate our value of L. The second step of the execution is simply to write down and highlight your final answer. In this problem, the one missing parameter for the design of our telescope was the distance L between the two lenses. Hence, as our final answer, we write down that the lenses must be placed 36 centimeters apart. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. The problem required us to find the distance L between the two lenses. This is exactly what we've provided. We verify that this distance is given in centimeters, which is the unit that is used throughout this problem. As a final overall check, it is good to sketch a ray diagram showing all of the lenses at once. Here is our primary object, which is to the left of lens number 1, and this produces a real image to the right of lens number 1. Lens number 2 is placed in such a way that the convergence of the beam to lens number 2 occurs to the right of lens number 2. That is to say that the object for lens number 2 is a virtual object. The diverging lens causes this beam to diverge, and in this case the diverging beam converges at a point to the left of lens number 2, which becomes a virtual image for lens number 2. I should point out that this diagram is at approximately the correct scale. Here is the overall solution. Top class. Here once more are the 3 steps of our problem-solving method. Thank you for watching.